Ever looked at a thermometer and maybe wondered, what was Earth's temperature like, say, hundreds of millions of years ago? Today, we're doing a deep dive into exactly that. We're exploring a really fascinating study called Earth's Ancient Surface Temperatures, a 485 million year history.
Yeah, this is new research led by Emily J. Judd and her team, and it uncovers some, well, truly surprising details about our planet's deep past. It definitely challenges some of the things we thought we knew.
Okay, so our mission for this deep dive, let's unpack their innovative approach first, and then see what these ancient climates actually reveal about Earth. So how on earth did they reconstruct temperatures over, what, 485 million years? I mean, no thermometers back then, right?
Right. That's the million-year question, isn't it?
Yeah.
Judd and her team used what scientists call proxy data.
Proxy data. Okay.
Think of them as natural chemical clues. They gathered over 150,000 of them from tiny fossils and compounds.
Wow, 150,000.
Yeah, things like oxygen isotopes in ancient shells or specific molecules preserved in old sediments. Each one is like a tiny sensor from the past. And crucially, they filtered all this data very carefully for accuracy.
Okay, so if I'm getting this right, these aren't direct measurements. They're more like natural records. Biological, geological clues that sort of encoded temperature info. That sounds like some serious scientific detective work.
Precisely. Yeah, detective work is a good way to put it.
Yeah.
And they didn't stop there. They took these proxy clues, right, and integrated them with powerful climate models. Get this. They ran simulations covering over 2.5 million years.
Oh, 2.5 million years of simulation time.
Incredible, isn't it? Their whole approach, they call it Phanerozoic data assimilation, FANDA for short.
Fandiacachi.
It is, and it basically merges those ancient clues, the proxies, with the predictive power of the climate models. This gives, well, probably the most robust picture we've ever had, and it carefully accounts for tricky things, like how ancient seawater chemistry might have affected the signals.
Okay, so they've got this groundbreaking method, Fanday. What did it tell them? What were the big surprises about Earth's ancient climate? Did it match up with older ideas, or did it shake things up?
Well, this is where it gets really interesting. FANDA shows that Earth's climate was actually more variable and often warmer overall than a lot of previous reconstructions suggested.
More variable and warmer.
Exactly, especially during what we call greenhouse intervals, these long stretches when Earth was much warmer, often with little or no ice at the poles. So this really refines our picture of just how warm Earth could get.
That raises a big question, though, doesn't it? If it was generally warmer, how does that square with the evidence we have for ancient ice ages? We know there were massive glaciations at different times.
That's a really sharp point. And it's fascinating. Even with a global mean surface temperature, GMST, around 21 degrees Celsius,
Okay.
which is way warmer than today's average, maybe 14 degrees or so.
Right, much warmer.
Even then, Earth could still support extensive ice sheets, huge ones. The key isn't just the global average number, it's paleogeography.
Paleogeography. You mean the layout of the continents back then?
Exactly, the arrangement of land and sea. For instance, during the Hernantian period, this massive supercontinent, Gondwana, it was positioned near the South Pole, allowing cold conditions to spread to lower latitudes. So you could have these vast ice sheets, even with a higher global average temperature.
Ah, okay. So the global average, the GMST, doesn't tell the whole story about where ice can actually form.
Precisely. It's an average, right?
Yeah.
Heavily weighted by huge, warm tropical oceans. And you see a similar thing with the extreme heat periods, the hothouse climates, when you had massive, continuous land masses like Pangaea back in the Triassic.
Right, the one big supercontinent.
Yeah, that led to more widespread, really extreme heat zones inland. It just shows how much local geography, land versus ocean, shapes climate patterns way beyond just that single global average number.
So taking all this in, what's the big takeaway from this deep dive for how we understand Earth's climate history?
Well, I think it really highlights how sophisticated science keeps refining our view of the past. It's not static. This Fan-de-A approach reveals nuances how things like where the continents were or ocean currents drove climate in ways a simple average might hide. It just underscores the incredible complexity, the dynamism of our planet's climate system over these vast timescales.
It really puts things in perspective,
Yeah.
knowing how Earth's climate has shifted over 485 million years, seeing how profoundly continent placement mattered. What questions does this leave you pondering about our planet's future and maybe how we think about climate change today?